Imagine you landed on an alien world and you're trying to figure out a way to communicate to the people there. We think that the easiest way to communicate to these people would be through mathematics. That is the main thrust of what abstract algebra is about. It's about learning the deeper principles in our mathematical structures so that we could apply them to other contexts. Let's get started. I'm going to start with a context that you're probably familiar with, and we're going to use that as a way to define what we mean by a group, and then look at other contexts where these same principles apply. All right, we're going to look at Z4 with operation addition. A quick look at what Z4 is just you can consider the numbers 0, 1, 2, 3 with addition mod 4. And what they are actually representing here, for example 0, is representing anything that is congruent to 0 mod 4. So it's actually a lot of stuff packaged in the box that we label 0. And so Z4 is just, we're just operating with the boxes. What I really want to do is look at Z4 and its addition, and we're going to use that to point out some interesting principles to extrapolate to other group contexts. So adding 0 is pretty easy, right? So I add 0 to 1, 2, and 3, I just get 1, 2, and 3. And that's true on the left and the right side. 1 plus 1 is 2, 1 plus 2 is 3, and here's our first interesting addition example in mod 4 is that 1 plus 3 is not 4, it's 0, right? Because remember, 4 is in the box labeled 0, so 1 plus 3 is 0. 2 plus 1 is 3, 2 plus 2 is 0, and then 2 plus 3, which would be 5, 5 is in the 1 box because 5 and 1 are congruent mod 4. For the last row, we have 3 plus 1 is 0, 3 plus 2 is 1, and 3 plus 3, which is 6, would be 2. All right, so here we quickly did an addition table for mod 4. We call this a Cayley table, and Cayley tables can help us look at kind of the symmetry of whatever our context is, but I want to point out a few things here. Notice, first of all, that this 0 element was special because when I added anything to 0, nothing got changed. We call this an identity. So here 0 operates like the identity. It's just when I apply my operation, my original thing does not change. Another thing I want to point out is that for each element, I could add it to something and get 0 again. So for example, if I take the element 1 and I add it to 3, I get the identity again. All right, so we can say for any a in Z4, there exists an a to the negative 1 power, which would mean a inverse in Z4, such that when I add a and a inverse together, I get back to 0. So this principle that we're looking at now is called inverses. Z4 has an identity element, and every element has an inverse. That's essentially what we need to define a group. Let me show you that formally. Okay, so we're going to let G be a set with some binary operation that we'll represent as star. Then G paired with that operation is a group if the following hold. Now this is one thing we didn't check on our last example, but we do need that our star is associative, meaning that if I star A and B first and then C, I get the same thing as if I do B and C first and then A star that. We need an associative operation. Outside of that, we also need an identity element. So in our previous example, 0 was that identity element where we call it E in general terms. A star E is the same as E star A, and it just leaves you with A. So something plus 0 is the same as 0 plus that thing, and it's just the original thing, right? Nothing changes. The third thing that we need is that for any element A, there is an A inverse that gets us back to the identity element when we use star. So that is that everything has an inverse element that we can get back to our identity. If we have those three things together, then my set with my operation is a group. And we can attach one more adjective to groups, and that is if star is commutative, so if A star B is B star A for all my elements, then we say that G is an abelian group. So was our previous example a group? I think so. I mean, addition we know is associative, okay? We had an identity element and everything had an inverse. And in fact, you can tell by the symmetry of my table, since it's symmetric about this diagonal here, It's actually an abelian group because that means that my addition is commutative. For example, 2 plus 3 was the same as 3 plus 2. And we could do this with any pair of elements. So this is not only a group, it's an abelian group. So as for an exercise, we want to list some common groups. We already know one. We know Z4 with addition is a group. So I'm going to make a table and just to look at some of these. So we can start with Z4 with addition. We know it's associative. We said the identity element was 0 because something plus 0 is that thing. And we have inverses. We could say maybe negative A, or I used A inverse. I used A to the negative 1 power earlier. Those mean the same thing in this context. And then we knew it was an abelian group. So this is a group, Z4. What else could we do? What about, could we do just the integers? So the integers period. So maybe with addition. So we know integer addition is associative. We know we have an identity. And inverses, 2 plus what is 0 in the integers? Negative A is my inverse, right? So we could say, for example, 2 plus negative 2 gets me back to 0. And this is actually an abelian group as well. So the integers with addition form an abelian group. What else could we do? What about if we did the integers with multiplication? Well, I know integer multiplication is associative. That's not a problem. Is there something, like if I say 3 times something equals 3? Yes. 1 operates as that identity. Okay. However, let's think about inverses. 2 times what would give me back to 1? 2 times 1/2 gives me back to 1. However, 1/2 is not an integer. So we fail on the inverse property. We have no inverses with the integers with multiplication. It would be, if it were a group, it would be abelian, but it's not a group. Okay, well, what else could we do? Maybe we could do the real numbers with multiplication, because then we do get these inverses. So it's associative. We have an identity of 1. We do get inverses. Well, hold on now. There's one thing I got to worry about. What about 0? 0 times what gives me 1? Nothing. So the real numbers are also not a group. But what if I did this? The real numbers throw out 0 with multiplication. So now it's associative. We have an identity. And anything other than 0, so for example, pi times 1 over pi gives me 1. I have identities. And it's abelian. So here we have the real numbers without 0 with multiplication is also a group. And there are plenty of other groups out there. Now remember, what we're trying to do is find these underlying truths of some of these structures and how they work. And associative operations, identity, and inverse are key components to doing mathematics in a safe environment, in a group. And the abelian characteristic makes it even easier. So let's look at some other examples. All right, this time we have a set S, which is 1, negative 1, I, and negative I with operation multiplication, and I want to know, is this a group? Okay, so we're going to go through our properties. We need to know, is it associative? Well, this is just multiplication in the complex numbers, which is similar to multiplication in the real numbers, which is associative. Do we have an identity element? Well, I think anything times 1 is just going to stay the same. So I think the identity element would be 1 here. The only real question I have is, do we have inverses? And so to answer that question, I think we're going to just fill out a Cayley table. And what I need is that for each row and column, the 1 shows up somewhere. Okay, now when I write I here, just remember, we do mean that I squared is negative 1. This is I like the imaginary unit, and that is what we mean here. So if I multiply by 1, we already know that that's not going to change. So I have 1, negative 1, I, negative I. I can go across the first row and the first column. Now if I multiply by negative 1, that one's pretty simple too. Negative 1 times negative 1 is 1. And we get negative I, and then negative I, which is positive I. Now we need to multiply I times I. I times I we define as negative 1. So I times negative I is negative I squared, which is negative 1 that I like to call positive 1. So negative I times I is positive 1. We get that on both sides. And then lastly, negative I times negative I would be positive I squared, which gives me negative 1. So here's my Cayley table. And you may have noticed already that each row and column has a 1 in it. So everything has an inverse. We do have inverses. Is this a group? Yes, this is a group. And in fact, it's an abelian group. Because you can see the symmetry in my table here. It didn't matter which order I did my multiplication, I get the same thing. This is an abelian group. Before we move on to some other examples, I've got a couple more exercises that I would like for you to look at, and the solutions to those are at the end of this video. Okay, let's look at another example. Here we have, we call this GL2. That means the general linear group of 2 by 2 matrices with real number entries, and these are the invertible matrices, which means that they have an inverse. So we want to know, does this form a group? Okay, now if you've had linear algebra, then you know that this matrix has no inverse, which means it would not be in this set. Checking down my list, is GL2 associative? Yes, matrix multiplication is associative. Do I have an identity element? Yes. If I multiply a matrix by 1, 0, 0, 1, then that matrix, the result of that multiplication is what I started with. This is my identity element. Do I have inverses? Yes, I don't have to exactly label what they are because I said that this is the set of invertible matrices, meaning that they do have an inverse. But if I want to know the inverse of the matrix ABCD, you just flip the entries along one diagonal and make the other diagonal negative, and then you divide by the determinant, which is AD minus BC. So this would be the inverse of the matrix ABCD. We have inverses. So this thing is a group. However, it's not abelian because we know in matrix multiplication, AB does not necessarily mean B times A. So this is a group, but a non-abelian group, which is pretty interesting. All right, let's look at another example. Now I have a weird set that I call U12, and this is the set of things in Z12 that have greatest common divisor with 12 to be 1. And I want to know, is this a group of multiplication? Now in general, things like Z4 with multiplication is not a group because, well, 1, you have the 0, so we need to throw 0 out. But even then, some elements like 2 have no inverse because 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 0, and 2 times 3 is 2 again. So 2 has no inverse. So Z4 with multiplication is not a group. What about U12? I guess we need to figure out kind of what U12 is. This is the things in Z12, so we're going from 0 to 12, but have greatest common divisor of 12, 1. In other words, it's relatively prime to 12. So 0 is not in this. 1 is. What about 2? GCD of 2 and 12 is not 1. 3, no. 4, no. How about 5? Okay. GCD of 6 and 12 is not 1. 7, definitely. 8, no. 9, no. Right? GCD of 9 and 12 is not 1. 10, nope. How about 11? Yeah. And then 12, no. Okay, so I'm just looking at the elements 1, 5, 7, and 11 with multiplication. So is this a group? All right, let's see. Associative, yes. Multiplication in Z12 is associative. Identity, yes. We have the 1. 5 times 1 is 5, etc., etc. The only question then is, do we have inverses? And so to do that, we can just use a Cayley table to figure out if this is indeed a group. And so you have to do multiplication mod 12. 5 times 5 is 25. That's 1 mod 12. 5 times 7 is 35. Let's see, mod 12, that would be 11. And 5 times 11 is 55. mod 12. So I'm just subtracting multiples of 12. So 55 minus 48, you get 7. Okay, 5 times 7 would be 11. 5 times 11 is 7 again. 7 times 7 is 49. Just subtract multiples of 12 to get something between 0 and 12. 49 is 1 mod 12. 77. Subtracting out multiples of 12, we end up with 5. And then 7 times 11 is 5. And 11 times 11 is 121, which is 1 mod 12. So notice every element has an inverse. In fact, every element is its own inverse. So yes, we do have inverses. So this is a group. And in fact, it's an abelian group because the multiplication is commutative. We call this group the group of units. Now once we understand the definition of the group, we can do some pretty amazing things and make blanket statements about groups as a whole. So that would apply to all these different contexts. So we'll look at more of that later. Thanks for watching. Let me know if you have any questions.